Hello Grade 12 GED 2019-2020 students. Our lesson for today is 2.4 as mentioned in your syllabus, standing waves in stretch strings. Here are the objectives: to define standing waves, to show the formation of standing waves in stretch strings, to study the characteristics of standing waves, to derive the general expression for the frequency of the nth mode of standing waves in stretch strings, to calculate the speed of standing waves in stretch string. As a definition, a standing wave is the result of interference between two waves of equal frequency and amplitude traveling along the same line with the same speed but in opposite directions. Now let us come with the important words here in the definition. You have here a result of interference between two waves of equal frequency and amplitude traveling along the same line with the same speed but opposite direction. This will take us to the superposition of two waves. You know that if two or more waves, we are only here talking about two waves, if two waves meet at a point, the resultant displacement at that point equal to the sum of the displacement of each individual wave at that point. That's it. That is, if the two waves arrive in phase, and what is in phase? We mean that the crest of one wave arrive at the same time with the crest with the other wave here, or the trough of one wave meets the trough of the other wave at the same time, then a constructive interference will occur here. The resultant displacement of the wave at that point will be the sum of both displacement here. So if both crests have the same amplitude A and A, this higher crest will have an amplitude of 2A. Here, if the amplitude is A and A here, the deeper trough will have an amplitude of AA. So here, in the case of forming a constructive interference. But if the two waves arrive at the same time, if a crest arrive at the same time that a trough of the other wave, here a destructive interference will take place. Here, as you see, that they are anti-phase. The resultant displacement at that point will be 0 if both have the same amplitude. Now, this is a simulation which shows the formation of standing waves. We have here a green wave which is moving to the left and a blue wave which is moving to the right. So we have two progressive waves moving at the same line, on the same line in opposite directions, having the same amplitudes and having the same amplitude and frequency. The resultant wave as a superposition, so the resultant wave is the black color wave. We call this black color wave a standing wave. Why it is called a standing wave? You see here, the blue and the green waves are progressive waves. They are moving and carrying energy towards right or left. But the black colored wave is not propagating towards right or left. The particles of the wave are only moving up and down. So the energy for this black colored wave, which is standing wave or stationary wave, the energy does not propagate. Here you can see for some points the two waves, the blue and the green wave, they are meeting each other at this point, and they are always in phase. It means here the particles of the blue and the green waves are moving together either down or up. So they are, as a result, there is a higher trough, a deeper trough, or a higher crest with an amplitude or displacement as double of the displacement of each individual wave. This is also happening here and here. So the black colored wave, which is a standing wave, having maximum displacement at these points because the particles of both waves at these points are moving in phase. So these points are antinodes, AN. Here at these points you can see both waves are in anti-phase. It means they are, one is moving up, the other is moving down. The particles, I mean, if the particle for the green color at this point is moving up, so the particles at the same point for the other wave are moving down. So with a phase difference of 180. So here the resultant wave will have a displacement of 0. These points are called nodes. So also we are going to get the same stationary wave on a spring. Here we have a fixed point. An outward pulse has been sent to that fixed point. When it comes to the fixed point, it will reflect as a trough, the crest will reflect as trough. If another outward pulse is sent, so we will end with two pulses which are moving in opposite directions, having the same amplitude and same amplitude, of course, the same speed and the same frequency. So as a result of the superposition of both waves, we will get standing wave. This is again a diagram showing a standing wave which is colored in black, and it is a result of the superposition of the blue and the red waves, which are moving in opposite directions and having the same amplitude, frequency, and speed. So again, as you see here, we are having some points, then some stationary points with no displacement, yeah, and other points here which are having maximum displacement, which called antinodes. These red color points are called nodes. Actually, this is a typical diagrams for standing waves. Always standing wave between two fixed points and with nodes. Here a node, here a node. This is forming one loop. This is called loop. This is standing wave forming two loops with 3 nodes and 2 antinodes. 3 loops, 4 loops. Now, let's come to some concepts about or characteristics about the standing waves. As we said that the nodes are the points that do not move with no displacement. The points where the wave or the particles oscillate with maximum amplitude are called antinodes. The phase difference and amplitude. Also, we mentioned that nodes are formed when the two waves are in antiphase or out of phase. So then the waves interfere destructively, giving zero displacement. For the antinodes, the waves are in phase when the waves combine constructively, giving the amplitude twice that of each wave, because they have the same amplitude. The wavelength for a standing wave here, the separation between two adjacent nodes here, this or this, will give us half an amplitude, half a wavelength. Also, the separation between two adjacent antinodes is lambda over 2. So we will find that the wavelength for a standing wave is the separation between 3 successive antinodes or 3 successive nodes. Here, now we want to calculate the speed of standing waves in stretched strings. Practically in the lab, you will, when you are doing the experiment of standing wave in stretched strings, this is the formation or the shape of standing wave that you are going to get. 1 loop, 2 loops, 3 loops, and so on. This is a vibrator, and here it's a fixed point where the string is going over a pulley and stretched by some weights on the other hand. So standing waves here in stretch strings are formed also in some stretched musical instruments like guitar. So listening to different notes is coming from forming different frequencies. So we want to calculate the frequency of different mode of vibrations or notes for standing waves on a stretched string. Then we will calculate the speed of standing wave for the stretched string. Now students, let's us go to get an expression for calculating the frequency of the nth mode of standing waves in stretched string. We have different modes of vibrations here. The first mode, second, third, fourth. So first mode with 1 loop, here with 2 loops and 2 antinodes, 3 loops with 3 antinodes, and so on. This is also called the fundamental mode. Now here, if you see that the length of the string is L, which is fixed. So L here, to calculate the frequency, we have to get the wavelength. We are going to calculate the wavelength in terms of L, the length of the string. Here, our length, if you see here, our length is half of a lambda, which is the separation of 2 adjacent nodes. So this is half of a lambda. Here we have the same length equal to 2/2 of a lambda. This is 1/2. This is another half. 2/2 of a lambda, which is actually it is lambda. We will write it in this term to come out with a general expression. So there are different lambda here for different modes for a fixed length. So we will call this lambda 1, this lambda 2. Here we have 1/2, 2/2, 3/2. So 3/2 of lambda. This is lambda 3. So we can find here that for a general expression of L equal to 1, 2, 3. 1 lambda over 2, 2 lambda over 2, 3 lambda over 2. So it is n lambda n over 2. From here we can get our lambda. So for lambda for any mode of the vibration, which equal to 2L over n. So one can find that from here our lambda 1 equal to 2L. Yes, and here our lambda 2, this is lambda 1, lambda 2 is equal to L. Lambda 3 equal to 2L over 3. So lambda always equal to here 2L, 2 over 2L, 2 over 3L, so 2 over NL. Now, to calculate the speed of a standing wave, we have to use our general equation for wave, speed of wave, f lambda. So to come out with an expression for frequency, our frequency for any mode f vibration equal to v over lambda. So substituting lambda from here, we can get that Fn equal to V over 2L here. Okay, now let's do some examples. Here in this diagram, we have a standing wave on a string. The length of the string and the wavelength of the wave are. So we have to calculate L and lambda. This is L, the length of a string. I think first we have to calculate lambda. Here you have the separation between two adjacent antinodes, which forms half a lambda. So our half a lambda equal to 0.25 meters. So our lambda is equal to 2 times 0.25, which is equal to 0.5 meters. We have here 0.5 and 0.5, so we have to determine L to get the correct answer. Going back to the expression for L, which is equal to n lambda over 2, so our L equal to n lambda over 2. So we have here 4 loops, 4th mode of vibration, so 4 times lambda over 2, okay, which is simply equal to 1 meter. So this is our correct answer. For the second example, suppose that a string is 1.2 meters long, so L equal to 1.2 meter, vibrates in the 3rd mode of vibration, so we have only 3 loops with n equal to 3. Determine the speed of the wave. Okay, so if the frequency is 50, so frequency is given as 50 hertz, so we have to calculate V. To calculate V, we have to use V equal to lambda F. F is there, but we have to calculate lambda. Our lambda, going back to the expression for lambda, is 2L over N. So lambda is equal to 2L over N. Okay, we have 2 times 1.2 over, so 2 times 1.2 over N, which is 3. This will give us 0.8 meters. Okay, so we have here 0.8 times our F, which is 50, will give us 4 meters per second. This is the end of our lesson. The next lesson will be standing waves in closed tube.